A couple of weeks ago I did a teardown on the GE Link LED light bulb, and I posted that on YouTube, and one of the viewers had a question asking if the RF module had a amplifier external to the main chip, system on a chip, or not. And so I looked a little closer at the RF module, which is this little guy here, and we'll try to get focus on that. And if you look down here, you see the antenna comes in, and it does go through some passives here, but it goes right into the RF output pin on the chip. So there's no amplifier inline anywhere on that antenna. So then he started asking, his name is Dat Tran, I believe, and he started asking if, well, maybe there's an amplifier on the hub side of things. So I decided to take apart the Wink hub and look a little bit deeper into what all is involved with that, and the answer does come through. So we're going to go ahead, and right here we have the Wink hub. It's pretty big. I think it's oversized. I'll go that way. So the thing's about 7.5 inches square. And I thought for something like this, even though it does have support multiple protocols and all of that, still seemed pretty big. So I went ahead and opened it up, and I've already taken the screws out of here. Get the camera down a little better. So I'll take the cover off, and I've already taken the cans off, the shielding off of the main CPU and the power regulation area here to get a better view of that and to speed the video up. So if you look at the board, there we go. If you look at the board, you have the main CPU area here, you have power supply, or part of the power supply, there's some over here too, and then you have the 2.4 gigahertz Zigbee, the 433 megahertz Kitty, 915 megahertz Z-Wave. It's a misprint on the stencil, I think. But and then 2.4 gigahertz Wi-Fi Bluetooth, and then the 433 megahertz Lutron. And looking at this is kind of strange. A lot of these modules, I'll say a couple of them anyways. The Kitty has a PIC microcontroller which runs the radio, and we'll get into that in more detail. And then the Lutron's the same way, except it has an ARM processor which runs the same radio that they use for the Kitty. It's actually the same chip. But I'm kind of surprised that they're not using the main microcontroller and talking directly to these RF chips rather than going through this this ARM processor and this PIC here. Processor has a 1 gigabit flash RAM here, and it's also got a 512 megabit DDR2 memory, so it's quite capable processor. So it should have no problem controlling these radio modules. So I'm going to go ahead and I'm going to go through each one of these RF modules, and we'll have a quick overview of what chips they're using and how they're set up. So the first one we're going to start with is a 2.4 gigahertz Zigbee, and I'm going to lay this down. I'll get the camera overhead. So this is the 2.4 gigahertz Zigbee. What the link lights use. So it is the controller for these little boards here. And the main chip that you're looking at here that I'm pointing to, it's a Silicon Labs EM357 802.15.4 system on chip, 32-bit ARM Cortex M3 processor, 12 kilobytes of RAM, AES 123 encryption accelerator, UART SPI, 2-wire interface, has 24 GPIOs. It's got a, built in this chip is a 2.4 gigahertz IEEE 802.15.4-2003 transceiver with -100 dBm to -102 dBm receiver sensitivity configurable, and a +3 dB normal output configurable up to 8 dBm. This is a 2.1 to 3.6 volt chip with an internal 1.8 and 1.25 volt regulator on it. So, in a lot of ways, although this uses a different chip, it's got a lot of the same features. Now, we'll move over to this chip to the right, and that's an Sige 2.4 gigahertz Smart Energy Zigbee RF front-end module. It's 2 volts to 3.6 volts operation. Has an integrated power amplifier up to 24 dBm output power, as well as integrated low noise amplifier LNA with a programmable bypass and diversity antenna switching on the TX and RX. So that answers that trans question as to whether the Wink hub on the Zigbee had a power amplifier. It does, and that's right there. Here you can see the antenna comes out, and it's shielded with these shielded on either side with the ground plane. It comes out and comes to the antenna here, and there's another one on 2, and I see that on most of these built-in antennas. They have the 2 leads. I'm not an RF guy, so I can't help you out a lot with how exactly that antenna works. So next we're going to move over to the Kitty. I think I'm pronouncing that right. It's Kid or Kitty. Transceiver here, and you see they use these antennas wound on it's on a plastic form, just a coil of wire soldered into the board, and the antenna feeds in over here through all these passives and to the main RF chip. The main controller chip for this section, the microcontroller, is a PIC16F883-I/SS 8-bit programmable microcontroller. It's got 7 kilobytes of program memory, 256 bytes of EEPROM, and 256 bytes of RAM. That is connected to the TI, here we go, the TI CC110L. It's a value line RF transistor from Texas Instruments. It's rated for 300 to 348 megahertz, 387 to 464 megahertz, 779 to 928 megahertz via an on-chip frequency synthesizer. It's got a baseband modem built in. It rates up to 600 kilobits per second. It's got a 64-byte receive and transmit FIFO, and operates with an SPI interface. That transceiver chip has a programmable output power up to plus 12 dBm, and it has a negative 116 dBm receive sensitivity at 0.6 kilobits per second. The chip supports 2 FSK, 4 FSK, GFSK, MSK, and OOK. And if you have any more questions about the layout on that, probably look at the chip data sheets. I'm going to link them at the bottom of this video so you can click on the data sheets and see what the chips are. It's kind of cool to be able to look at this and see what all these different transceivers use, and kind of get an idea for their features and functionality if you ever plan on doing some of this IoT stuff. Another thing to mention real quick is each section has its own JTAG, SPI, or other kind of interface on it. So you see the Zigbee has a JTAG SWD, the Kitty has an IDC debug, and that one there, I'm not sure what that is. It almost looks like a micro USB footprint, but I'm not sure. Obviously just another test port, setup port. The main processor, and I forgot to go back over that, does have a JPEG port. It also has a DUART, so it's got 3.3 volts on it, TX, RX, and ground. And I'm going to look at that later. I'm assuming it's a debug output, debug UART. So we might be able to pull some interesting information out of there. Next we're moving on to the Z-Wave 900 megahertz Z-Wave transceiver. And you can see you've got the Z-Wave SPI out here on the right, and then they've used a little secondary board with everything mounted on it. Assume they buy the module and install it. The main chip here, let me get in a little closer for you. It's a Sigma Designs SD3502A-CNE3. It's a general purpose Z-Wave system on chip, integrated microcontroller and RF module. It runs on 2.3 to 3.6 volts. It's got a 1000 step dimmer, 4-channel 12-bit rail-to-rail ADC, a 4-channel 16-bit LED PWM driver, 23 GPIOs, USB full speed SPI UART PWM, and is programmable via USB UART SPI. It's got hardware AES 128 security, and the transmitter output power ranges from -24 to +5 dBm. Our receive sensitivity is -106 dBm at 9.6 kilobits per second. It's capable of speeds of 9.6, 40, and 100 kilobits per second RF data rates, with frequency switching up to 3 channels. Chip also has 16 kilobytes of SRAM, 128 kilobytes of flash, and runs at 1 microamp when in sleep mode. Also has a built-in T-scanner and infrared controller. The smaller chip at the bottom, U9, is a ST95128RP. It's an SPI EEPROM, 16 kilobytes. So we're going to move on now to the, let's see if we can get this in here. There we go. This is the 2.4 gigahertz Wi-Fi, and I apologize that it's upside down. Top number on the chip is 1842E3, and the bottom was E623A1, it looks like. And I wasn't able to find anything on this chip. Looking at it, it looks kind of like a stacked layered, so it's probably some kind of hybrid module. But if you have any information on that, if you look at the, actually see if we can get the side in here. Yeah, you can see it's not your standard looking chip. So it's probably some custom BGA hybrid, would be my guess, but I'm open to suggestions. And then that comes out to the little 2.4 gigahertz antenna. So unfortunately not a lot of detail on there. Next we're going to move over to, there's a little status indicator LED. And that's one thing you notice about a lot of these little modules, they all have little indicator LEDs all over them, which you can't see when the case is closed. So I'm going to fire this up. We'll try a few different things with the case open and see what we get on the status LEDs. So here we have the Lutron JTAG. There's also, just out of frame here, a switch 3 for register. The only switch that's available when this is open is the system reset. Or, I'm sorry, the only switch that's available when this is closed is the system reset, and that's for the user to reset the whole system back to stock factory. I'm not quite sure what the register button is for. Haven't really looked into it. And get down here and try to get this chip readable. There you go, you should be able to read that. Main chip on the Lutron is an STM32L100RBT6. It's an ultra low power 32-bit Cortex M3, and I've linked it down below. It's got 128 kilobytes of flash, 10 kilobytes of SRAM, and 2 kilobytes of EEPROM. It's got a built-in LCD driver, USB 2.0, 2 SPI channels, 2 I2C channels, 3 an ADC, and a digital analog converter as well. It runs on 1.8 to 3.6 volts, and that's quite a powerful chip in itself. And we also have, let me turn this around so the light's not reflecting so bad. Looks like there's a spot there for an external EEPROM or something like that. And if you pan down, I'll try to get it centered here. This is the same, almost had it. Alright, this is a CC110L. It's the same chip that was on the kitty section of the board. And again, that's a value line RF transceiver from Texas Instruments. 300 to 348 megahertz, 387 to 464 megahertz, 779 to 928 megahertz with an onboard frequency synthesizer. And I won't go through all the other details on here, but seems like a pretty flexible little chip there. So that covers all of the transmission modules. Again, like I said, it's strange that you have such a capable chip over here for the main processor with lots of RAM and basically drive space on there, and they're still using another big Cortex chip over here, and then the PIC over on the kitty section of the board to run the RF. I'd be kind of curious why they did that, as opposed to just putting as much stuff as possible on the main processor there. So that's pretty much all the technical details on the ICs here. Like I said, I'm going to go ahead and I will fire this up, and we'll interact with it and watch how some of the lights blink and stuff like that. So I'm going to go ahead and put it back in the box so we can stand it up. It should stay there. And then get some power to it. And right now you can see when they boot this thing up, it comes up with this pink light. And it'll attempt to link to my Wi-Fi network, so right now it's going out over the Wi-Fi Bluetooth, and it'll turn solid blue once it's got a link to the Wi-Fi and also a link to the Wink Hub servers. If the servers aren't there, this thing doesn't work. I don't really like that. So I might be looking at other options, but for now we'll, there we go. So now it's linked on, it's connected on the Wi-Fi, and it's connected to the Wink network, as it were. I'm going to go ahead and synchronize a light bulb here, and we'll watch an eye on the, keep an eye on the TX RX outputs here, and then I'll figure out a way to get on these debug port and see what we can pick off of there. It is 3v3, so I'll need to set up a level converter to plug that into a laptop or whatever. Alright, so to connect on the what I believe are the debug ports here, I'm going to use this little COM port adapter board. It's actually part of the Cypress Semiconductor PSOC4 prototyping kit, and originally comes connected. These things are such a low price, it's great to get a cheap little serial adapter with them as well. So sometimes I just break them off, and it turns into a little $4 or $5 serial adapter. So I'm going to use that for this purpose and connect that up, and we'll see what we get out of this possible debug port when this thing's running. So good news, I was able to get the debug to work on this. I used a little 3-pin connector attached to my Ethernet to USB to serial adapter over there on the side, and basically what I have to do is power on the Wink hub and then connect the lines, and I'll show you what comes up on the screen here. We'll just get the camera on the screen. And here we are into the boot sequence. See everything coming up, showing lots of details. I'm sure you could dig through this. Apron Home Automation Gateway version 1.2. Interesting. Alright, so it looks like this thing's all booted up, connected to the network. I'm going to go ahead and turn a light off and on here. There's a light off, a light on. I'm also going to try discovering a light. So we'll add a new product, lights, GE link. Alright. And then now we're in learn mode. Turn the light on, and we'll see if it picks it up. Looks like it's not going to. I'm going to have to reset the light. The reset a link bulb is just off for 3 seconds. On for 3 seconds. Off for 3 seconds. On for 3 seconds. There we go. Now the light has reset. And the hub just found the light. And a whole bunch of stuff just happened there, but that resulted in now have GE light bulb. That's the one sitting right here by the computer, so we can turn that off. And turn that back on. So there you go. That's the Wink hub, working with the link lights and pulling debug information off the debug header. Hope you guys liked that and found it useful. If you did, please let me know. And I'll try to get more videos like this of interesting stuff, hopefully. Thanks. Bye-bye.